Hi everyone, and welcome to ENGR110 Lab. So unfortunately, again, we're going to be remote this semester, but I wanted to try to give as much of an in-person and hands-on experience as we can remotely. And so I just wanted to give kind of a brief introduction on the basics of what we'll be doing in this lab. Again, the primary focus of this course is designing experiments, doing statistical analysis, figuring out propagating error and uncertainty, determining precision error, bias error, and measuring basically physical quantities in this class. And one of the ways that we're going to utilize this is when we run experiments, we are going to do live data collection. So that's going to require the use of a data acquisition device. This is a Vernier sensor DAC. This is the data acquisition device that we'll be utilizing throughout these experiments. You'll notice in some of the labs coming up, specifically the Helmholtz lab, I use a National Instruments, a different type of DAC, but it's the same concept. We're going to acquire data live. So that's the whole idea behind this course. Live data as a function of time, you're going to analyze that and measure those physical quantities. So one of the key things we have to do in this lab is communicate with this DAC in order to capture the live data. So there's lots of tools that you can utilize to interact and interface with DACs. You could use Mathematica. You could use MATLAB is probably the premier tool for, it has a lot of built-in functionality in order to interface with data acquisition devices. So hopefully in the future we might be moving towards that. But one of the nicest and user-friendly and easiest way to communicate with DACs is through LabVIEW. So many of you may have used LabVIEW before, but if you haven't, it's a very attractive coding program for engineers. Why? Because it's very user-friendly and visual. So LabVIEW is actually kind of broken down. You can see here, this is front panel, this is our block diagram. It's the way that this coding language works is very, like I said, visual. So on the front panel, and I'm actually going to go ahead and one of the nice ways is if you have two screens, you always want to kind of break it down like this. But here I have my block diagram. You can imagine this is like kind of like the nuts and bolts, the guts of your code. So there's going to be lots of wires, diagrams, everything. Here, this is the front panel. So if you were building like an apparatus, this is what you'd want to show. You can see here there's these Boolean operators, there's these numeric indicators, controls, knobs, there's graphs. So everything you want to see visually, the output that you want to see, that is put on the front panel. On the back panel, you can look at, there's these structures, while loop, there's these array calculators, Boolean operators, if, greater than, numeric calculations, and specifically, we could save our files. We're going to use this function a lot, timing, but we're also going to use this to communicate with our DAC. So we're going to grab data with the DAC. We are going to communicate that. We're going to use LabVIEW. LabVIEW is essentially our tool. In this class, our analysis tool is going to be Mathematica. You could do the same analysis in LabVIEW, but it's fairly laborious. So I would definitely suggest using MATLAB, Excel, Mathematica for data analysis, and to create beautiful plots. But again, LabVIEW is going to be our tool to communicate with the DAC and more importantly, to save our data so that then we can process it later and write beautiful lab reports and do that. So throughout these labs, we're going to kind of show you the basics of the lab VIs that we're going to create. You are not required to do this, obviously, because you don't have your lab VIs and we're not sending these kits, but this will hopefully give you a better understanding of how the labs are going to work. So I'll see you in our next video for our first lab, which is going to be Thermocouple lab. You're going to make your own thermocouples. We're going to measure with the thermometers with thermocouples right here. You see I'm very clean and organized. So we're going to go ahead and do that in the next video. All right, I'll see you then. Thanks. Bye. All right, everyone, we are back and we are going to start our thermocouple lab. So what we're going to need for this lab is this container of ice, our Vernier thermocouple, which will be one of our measurement tools, our sensor DAC, the power cord for that DAC. We also need our instrumentation amplifier, our thermometer, which is our second measurement tool, and then finally this wire is our handmade thermocouple wire. So we are going to make our handmade thermocouple. That's going to be our third tool, and then we're going to measure all those different types of basically temperature conditions. So what we're going to do is start to kind of plug and put everything together. So first things first, let's go ahead and we're going to go ahead and hook this up. So into my Vernier instrumentation, our sensor DAC. I'm going to go ahead. Sorry for the. So let's go ahead and plug this guy in. So I'm plugging in right here. Now you probably can't see that, but it's not super engaging. as opposed to the rest of the slab, which is extremely engaging. So I'm going to plug in my sensor DAC. I have basically a cord right here for USB. That's going to be plugged right into our computer over here. So let's go ahead and around the front. So I'll plug this in right over there, just in the USB. So now we could connect and communicate with our DAC. You can hopefully see the power light is now blinking, so our DAC is functional. So you'll see that my DAC, my sensor DAC, has different channels. So channels 1, 2, 3, 4. So I have my vernier thermocouple. So it is a thermocouple that's already built up to kind of interface and communicate with this DAC. So here's the probe right here. So this is the vernier thermocouple. So we're going to put that to measure our materials. You can see it's welded together right there. Let's see if I can get a nice focus. Let's see. There we go. Now we're focused. So you can see that thermocouple basically probe right there. So all we're going to do is just plug this guy right into our basically channel 1. So let me plug that in, and you'll see it in all its glory in a second. So that is, so we're going to measure right here. Now, the one, and actually the only live measurement that we're not going to take in this class is going to be our analog, basically our baseline thermometer measurement. So what we're going to do is we'll stick this in, our temperature conditions, and we'll measure it live, and we'll provide those readings to you. And then finally, we're going to have to make our handmade thermocouple. So to do that, we're going to actually kind of set up, and then I'll show you in a separate video. All right? I'll see, or not a separate video, but in a transition. A very smooth, natural transition like this one. See you in the... So in order to make our thermocouple, our handmade thermocouple, I'm going to cut this already, our large wire, into 3 separate wires. You're going to see why in just a second. So I'm going to go through the probably a little bit unexciting stripping of the wires now. So I'm going to strip quite a bit of it because I want to kind of pigtail them together. So when you strip the wires, you see that this thermocouple wire is made of 2 wires. A copper wire, which unfortunately is in this blue marker, and this constant tan wire, which is in this red color kind of sheathing. So I'm going to have to basically strip this as well, but I'm going to do that just a little bit later on. So why do we have 2 different types of wires in this thermocouple? Well, if you read the lab handout, you know that from the Seebeck effect, we need 2 different materials to get the thermoelectric effect. We need 2 different materials because 2 different materials will have basically will develop different temperature gradients, and that will develop that resultant voltage as well. So that's kind of the basic concept of thermocouples, but they're very, very interesting materials. And as material science, you're actually going to kind of semi-calculate a Seebeck coefficient with this handmade thermocouple. So one of the things that you'll note about the handmade thermocouple, and when we take it into our kind of DAC as well, is that we are going to, the vernier thermocouple measures temperature. The here we can see actually beautifully sheathed. So again, that's constant tan. This is copper, obviously. So we are going to work with basically these 2 different materials, and we need that for our Seebeck effect. But when we measure, when we measure our vernier thermocouple, we're going to be measuring temperature explicitly. Oops, gotta be careful there. Same thing with our glass thermometer as well. But for our handmade thermocouple, we are going to actually get a voltage output. So we're going to have to do our first kind of air propagation there, and we are going to have to calculate and figure out how we're going to convert voltage to temperature. But we're going to do that using a 2-point calibration. So we're going to go ahead and do that. I'm going to kind of clean these up, and then I'll see you in the next transition smoothly. And I'm back. So I have successfully cleaned up all the wires. They look really, really beautiful, as you can kind of see here. So now what I'm going to do is I'm going to assemble my thermocouple. So my thermocouple needs a reference junction and a sensing junction. And I need to kind of measure the voltage, so I'm going to use my copper wire as my input to my power amplifier. So what that means is, for example, this is going to be my lead that goes in to my power amplifier. Now I could cut this guy off, or I could just kind of fold it here. So I'm going to fold this down because I'm only going to be worried about this guy. So I need this wire to basically go into my probes, my copper. So I'm going to take the other end of the same wire, and I'm going to fold back the constant tan as well. So I'm only going to be dealing with copper here. I'm probably going to cut this off a little bit later just to make sure there's no issues, but it's not a real big deal. So now I've got a wire, single wire here, here, and now I need to make my reference junction. So I'm going to take another wire, and again, I don't want to connect to the copper. I want to create my junction. So I'm going to basically pigtail my constant tin and copper. Now, you could also, if you would like to, you can also solder this together to make sure. But pigtail is gonna be appropriate enough for me. I'm gonna chop these off at the end just to make sure, again. But you can see here, right? So this wire is the beginning. So this goes into my power amplifier. Then this is my junction right here. So where the constant, the copper wire now is touching the constant tin here. So now this is gonna be either my reference or my sensor junction. And right here, actually I didn't snip this off completely. So now you get to see, just be cleaning this wire up. There we go. And actually here too. There we go. So this is connected to my constant tin. So now I'm actually gonna bend down the copper wire because I want a continuous, current. And then I'm gonna grab, again, my junctions need to be of 2 dissimilar materials. So this is my 3rd wire that I cut. I'm gonna fold down the constant tin now and then connect to my copper once more. So I'm gonna pigtail. I'm sure there's probably some electrical engineers that are just aghast that don't like me doing this, but I don't want them to blame my soldering technique either, so I'm kind of stuck. So here it is. That's it. So now we have our full material. So we'll see the handmade thermocouple once I clean this up. So I'll see you in the next smooth transition. And we are back. So you can see here again, lead, sensing junction, or reference junction, sensing junction, or vice versa. So this is where a mistake usually occurs in the lab. So if you read the lab handout, if you look at the kind of diagram, you're going to see that once we attach, for example, this lead into my negative terminal here, so I'm going to go ahead and put that through, and I'm going to tighten my probe here. Sorry, this is not exciting, but you can kind of see. So once I've attached this lead here to the negative probe, or negative terminal, now this, so I'm going to look at, so here's my wire going around. This is now my reference junction. This, which is attached to the live, or the hot, or the positive terminal, is going to be my sensing junction. So I'm going to just go ahead and put this through. Oops. Put this through one more time. Zoom out here. Now you can see all the glory of me turning this. There we go. Oops. Let me go ahead and just tighten. That's it. So I've got my handmade thermocouple. So now I'm going to go ahead and I am going to plug this into the 2nd channel. So we're all ready to go, except for the fact that, again, when we use this material, actually, when we use so we're gonna put our sensing junction, or reference junction, in 0 degrees C, so ice. So now we're ready to rock and roll. So I'll see you in the next video. We're gonna go through kind of a little bit of how we're gonna create our lab UVI. So right now we are gonna go ahead and create our lab UVI. So what I'm gonna do is I'm gonna put a waveform chart right here because I wanna see the data here. And I'm gonna label this as my vernier. So I'm gonna say VT, vernier thermocouple. I also want a chart of my handmade thermocouple. You can guess what I'm going to label that, HT. There's no live measurement for the glass thermometer. I'll be providing you that data elsewhere. So I've got 2 graphs right here and here. So I need to go ahead and first off build a structure, a while loop. So this means while this is running, or forever, until something happens, I'm actually going to add a Boolean. So this while loop is going to keep recording data until this is basically this if or. So until I press, actually, I'm going to add a stop button here. So here's a Boolean, and I'm going to add a stop. So if there's an emergency, I want to be able to stop my measurement. So stop this while loop, stop my measurement if I press the stop button, or if something else happens, X or Y. That's what's kind of happening here in this terminal. So either this or this happens. If this is true, then we're going to basically connect it to here. So if I connect it here, it's not going to work right now. But you can see here, when this arrow is broken in your lab VI, it's not gonna work. So, I now need to connect to my sensor DAC. So, what I'm gonna do, and you could I'm gonna go ahead and, I also wanna save my data, but we'll go there later. So I'm gonna go all the way down to my vernier sensor DAC, right here, Analog Express. I'm gonna drag it, I'm gonna put it here. And it's gonna do some thinking, and it's gonna say, it's gonna think even more, and it's gonna think even more. This is the excitement of real running experiments. So, you could see right now, the temperature that it's reading from my vernier thermocouple. 23 degrees, room temperature, pretty reasonable. Also, you could see, one of the other things, I set this power amplifier from 0 to 20 millivolts. So you can see here the value of millivolts right here for my handmade thermocouple. If I take out this reference temperature, we'll see what happens. Weird stuff starts to happen. So there's no temperature difference measured. Because again, this is our reference and sensor. So everything's working well. If this was negative, we'd flipped our materials. So people freak out when that tends to happen. So let's go ahead and I'm gonna go ahead and set the timing here. So I want to sample 10 seconds, every 10 seconds, great. And I'm gonna press OK here. So everything's kind of ready to go. So my first channel output, I want to go ahead and attach that to here, because that's my vernier thermocouple. My handmade thermocouple, that output's going here. And then once this is stopped, I want our basic experiment to stop. So once the 10 seconds have expired, it'll stop, or if I press the stop button, the experiment stops. And then we'll see the output right here. So we're all good, except for the most important step. I need to save my data. So let's write this measurement file. So this, I'm gonna label this. You could kind of see here. I'm gonna label this VT room temp, VTRT. You can see I'm gonna have a LMV file. I want one header only, one column only, et cetera, et cetera. You're gonna get the data files in Mathematica in a nicer format. I'm so kind, but you'll see that a little bit later. So I'm gonna also want to wire this output here to my save over here. And I'm gonna do the exact same thing for here. So this is not too exciting. I mean, data analysis is very exciting, but the minutia of this is not as exciting. So we're gonna go ahead and say HTRT. Handmade temperature, and then you could do 1 or 2 or 3, because again, you're gonna have multiple files here. So multiple tools, multiple temperature measurements. So one column only, and here we go. And then now I'm gonna wire this to here, and then there we go. All right, so now I can go ahead, you see here, my arrow's fine, so I can go ahead and run this experiment, and it'll go ahead and save. So it's gonna run, you can kind of see the values. Here. How are we going to convert these voltages to temperature? Well, we're going to do that in our 2-point calibration. But that's it. That's our first measurement. So we're good to go. Now we can go ahead and test and see and make sure that this is kind of working and functional. So I'm going to go ahead and unfortunately remove my glove. Or not unfortunately, but lab safety should dictate this. So we'll look at this measurement here. I'm going to go ahead and grab with my hand here. I'm gonna hold this, and then I'm going to have this play, and we'll see if the temperature rises. So I'm gonna go ahead and try to do this simultaneously. So it'll be the same for a second, and then let's see how it changes. Oh, my hand is very hot. I have sweaty palms for sure. So you look at the measurements the same. Or no, it's very, very different from our previous one. Now you can look at here, still we're seeing at about 9 millivolts, or 0.9 millivolts. So let me go ahead and do the same thing there. So I'm gonna grab this sensor junction. I'm gonna bring it a little bit closer. I'm still in the ice, so we're good to go. So let's do one more time. Let's have you, actually I'm gonna switch hands again. Sorry, I'm gonna use my left hand because I'm gonna use this to control here. So let's go ahead. It's gonna grab this. So I've just grabbed the junction, and as we anticipate, increase in voltage, increase in temperature, you're gonna kind of convert that. So that's essentially all we're doing in this lab. And again, we'll put our, you could confirm this with our glass thermometer as well. So if you look at here, right now, even though my hand is touching it, let me grab the other hand. So we're about like at 23, 20. So again, differences in the temperature measurements. So you're going to do a 2-point calibration at 0 degrees and then at 80 degrees C, or 100 actually, and then you're going to kind of figure out a calibration scaling factor to convert basically voltage to temperature. And yeah, that's it for your first lab. And write an excellent lab report. Make sure to give me an outline, give me drafts, let me see. Let's calibrate our expectations. Let's leave nothing, or let's reduce our uncertainty in this class, and then you'll do all fantastic. So I'll see you for the next video when we tackle Helmholtz coils and some patented information, and then frequency lab, and then finally strain gauge lab. See you in the next video. Thanks. Bye.